Every day, people observe phenomena which seem to have a precise direction of time. Waterfalls refracting in drops of foam, colored matter dissolving in water, rolling from the center in all directions. These examples all raise the same recurring question. Why do natural processes occur in one direction and not in the other? Why ahead and not behind? What is it that determines the arrow of time and the expansion of the universe and transition from order to disorder? What is the difference between past and future? Whilst time seems to flow in one precise direction in everyday life, fundamental laws of physics do not rule out the possibility for these processes moving back in time. Theoretically, a broken cup could recompose and jump up into the hand again. How can this paradox be explained? What is the origin of irreversibility and disorder? Ludwig Boltzmann was the first to give a convincing answer to all these questions. In the 1900s, many illustrious scientists didn't believe atoms existed. This may sound like a paradox today, since the 20th century is, after all, the century of great discoveries on the atomic nature of the world, from the electron to current experiments on elementary particles. Yet, prior to the tremendous progress of knowledge, Ludwig Boltzmann, an Austrian physicist, unknown genius and pioneer of atomism, had to struggle for nearly 40 years, the final years of the 19th century, to make his atomic vision of the world accepted. By the time his life was coming to an end, he was indeed considered a great scientist, the greatest within Austria. This, however, didn't seem to help.
Boltzmann è una personalità molto complessa.
Boltzmann's personality was complex and difficult to describe. He himself used to jestingly remind one that he was born during the night between Shrove Tuesday and Ash Wednesday.
Tra il martedì grasso e il mercoledì delle ceneri. Diceva che questo spiegava come mai,
thus explaining how his mood could swing so violently from being extremely happy to deeply depressed. Young Boltzmann used to be an enthusiast. But as the years went by, due to personal problems and uncertainty about decisions regarding his career, and possibly due to criticism of his scientific work, about which he felt very sensitively, he began to get depressed, to feel isolated.
Cominciò a sentire un senso di abbattimento, un'impressione di essere isolato.
In May 1906, the Dean of the Faculty of Philosophy of the Imperial Royal University of Vienna wrote a letter to inform the competent minister that Boltzmann suffered from a severe form of neurasthenia and had to give up all scientific activities. "Why don't we go on holiday by the sea?" his wife suggested, in Venetian, as Austrians used to say at the time. Sometime later, Henriette, with the help of some relatives from Gorizia, rented a house in Duino, a small and quiet seaside town near Trieste, a holiday destination for intellectuals and for the imperial family.
Nel settembre del 1906, poco più di 100 anni fa,
in September 1906, about 100 years ago, Ludwig Boltzmann came to Duino together with his beloved wife Henriette and his teenage daughter Elsa. Henriette expected much from this holiday, hoping that by relaxing and keeping away from work and conflicts, even academic ones, and by enjoying the sea, Ludwig could get out of the deep depression he had fallen into, and which worsened due to his physical suffering in that period, strong migraines, and above all, severe respiratory problems.
Boltzmann soffriva in quel periodo forti emicranie e soprattutto gravi problemi respiratori. Purtroppo queste speranze
Henriette's wishes did not come true, and Ludwig Boltzmann took his own life in that same place, Duino, in September 1906.
The day he died, he was feeling deeply troubled. While his wife and daughter were bathing, he put his intentions into effect. He used a short rope tied to the crossbars of a window frame. The first person to find his body was his daughter, Elsa. Many people were devastated by the news. A friend of Boltzmann, recalling that time, said, "The last time I visited him during the Easter holidays in 1906, he revealed to me his physical and mental suffering by saying, 'I could have never imagined such an end were possible.'" His wife Henriette lived long after him and carried that tragic day in Duino with her until the day she died in 1938 at the age of 85. At his death, Boltzmann was only 62. Ludwig Boltzmann was born in Vienna on the 20th of February 1844, the eldest child of a Viennese father of German origin and an Austrian mother. He came from a middle-class family. His father was a tax official, whilst his mother was the daughter of a wealthy merchant from Salzburg. Boltzmann grew up happily in a small town called Linz, where his father moved for reasons of work. There he attended high school, distinguishing himself for his talent in maths and scientific subjects. He used to spend most of his spare time playing the piano, his lifelong passion. Among his teachers was composer Anton Bruckner. Yet those happy years were interrupted by his father's sudden death when Ludwig was only 15. This tragic event would remain indelible throughout Boltzmann's life. Following revolts in different parts of the empire during the first half of the 19th century and the defeat of France and Prussia, Austria abandoned every imperialist ambition. In 1867, the empire was divided into the Austrian Empire and the Hungarian Empire. Thus, poor and rich, Slavs and Germans, Jews and Christians all lived side by side under the reign of the dynasty of Franz Joseph, who was to rule for 68 years. The emperor's old age and monotonous personality embodied the vain willingness to oppose the crumbling of the Danubian monarchy. The melancholy awareness of the imperial decline stood in contrast to light-hearted frivolity. Yet that dying world was trying to hide its decline through a sparkling sort of joie de vivre. The café, with its lively and intriguing atmosphere, was the symbol of the old Central Europe, a home and meeting place of poets, a place where ideas were exchanged, an artistic coterie and welcome refuge. During this period of relative peace and prosperity, Boltzmann began his scientific career. In 1863, at the age of 19, he enrolled at the University of Vienna as a physics and mathematics student, receiving his PhD only 3 years later in 1866. In 1867, Boltzmann became a lecturer at the Physics Institute, founded 14 years earlier by Christian Doppler. In 1869, Boltzmann was appointed full professor of mathematical physics at the University of Graz, which was amongst the most prestigious universities at a European level of that time. Physicists' education at that time mainly focused on mechanics, the science which describes the laws of the motion of bodies. Galileo Galilei was the first to introduce it during the 17th century. Isaac Newton, through his monumental work Philosophiae Naturalis Principia Mathematica, in which he formulated the universal laws of motion, extending them to the heavenly bodies, gave an impetus to mechanics which saw its major developments. Mechanics reached its peak during the early 19th century thanks to the scientific manifesto of Pierre-Simon Laplace. Laplace began his Exposition du système du monde, one of the most influential books in modern science, in this way.
An intellect which at a certain moment would know all forces that set nature in motion, and all positions of an item of which nature is composed, if this intellect were also vast enough, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes.
Mechanics indeed would be essential to Boltzmann's work in his studies aimed at understanding the nature of heat. At that time, scientists were extremely interested in the study of heat for two main reasons: a mere scientific curiosity on the one hand, and for applicative reasons on the other. The first half of the 19th century saw European society and economy experiencing deep changes. The Industrial Revolution had begun. The principal factor of the revolution was the steam engine, patented by James Watt in 1769. The machine consisted of a boiler which, through the steam produced by the boiling water, moved gears to produce mechanical function. The steam engine was initially used to extract water from mine shafts, but it soon replaced traditional horse-drawn vehicles. The way was paved for new revolutionary systems such as steamships and railways. The fast technological development of the steam engine halfway through the 19th century, however, was not followed by an understanding of the physical phenomena which determined its functioning. The following years saw scientists' investigations increasingly aimed at finding convincing answers regarding the origin of heat, energy, and its transformation processes. Experiments carried out by Joule, starting from 1840, were vital in proving the equivalence between mechanical work and heat. Thus, a new science called thermodynamics was born.
What is known today as thermodynamics had already begun during the second half of the 18th century. Why? Because scientists at that time had a big problem, which was everything but ingenuous. How does a thermometer work? A thermometer is an instrument used to measure something. But what? The scientific community of the second half of the 18th century was divided between two opposing standpoints. One of them, to which the majority adhered, and which was supported by a great scientist, Lavoisier, believed that the thermometer was an instrument which measured the quantity of a fluid called caloric. A small group of mathematicians, from Daniel Bernoulli to Lagrange and Laplace, opposed this dominant view and stated that a thermometer measured the average kinetic energy of particles of a gas or of a fluid. This, of course, created enormous problems from both an experimental and a theoretical point of view.
Sia dal punto di vista sperimentale, sia dal punto di vista teorico.
Thermodynamics has many founders but few laws. It is the result of the collective scientific work throughout the 19th century. Great scientists such as Lord Kelvin, who gave thermodynamics its name, Hermann von Helmholtz, Sadi Carnot, Rudolf Clausius, and Joseph Fourier played a leading role. Others contributed as well through their pure interest for science. It's the case of American adventurer Benjamin Thompson, future Count of Rumford, who understood that heat was the consequence of disordered motion of the fundamental constituents of matter. An essential intuition for Boltzmann's future work. Thermodynamics is based on two laws. The first declares that in any natural process, the total amount of energy remains constant. Energy may transform into heat or mechanical work, but it cannot be created or destroyed. The second law of thermodynamics, as stated by Rudolf Clausius, says that heat energy flows spontaneously from a hot body to a cold body, and not vice versa.
Al centro degli interessi di Boltzmann c'era indubbiamente il tentativo di capire la seconda legge della termodinamica.
Boltzmann's core interest was that of understanding the second law of thermodynamics. Let me add Albert Einstein's standpoint, which came much later. Einstein believed that the second law of thermodynamics, together with the notion of photons, weren't fully understood yet. What did he mean? Heat tends to move spontaneously from high to low temperatures. The student attending natural science lessons at the École Polytechnique during the early 1800s would have learned this fundamental law from Guy Lussac, which, however, lacked an interpretation. And finding an interpretation was vital because in those years Laplace used to teach at the École Polytechnique, and he had already perfectly understood that the great laws of physics are symmetrical with respect to time, and that they do not distinguish between past and future. So this second law was actually an enormous problem. Also related to the so-called entropy formulated by Clausius in 1864, who stated, "I chose the word entropy because it was so similar to the word energy, with a fundamental difference. Whilst the energy of the universe is conserved, entropy tends to increase."
Entropy, together with energy, is probably the most vital concept in nature. Energy remains constant. Entropy, instead, increases continuously. It can never decrease. This is exactly the essence on which the second law of thermodynamics is based. The entropy of a system of bodies may only increase. When brought to its maximum levels, it remains constant. If it increases, then the process is irreversible. If it remains constant, it is reversible and may even be inverted. This is the major difference between the laws of nature. Thermodynamical equilibrium occurs when entropy has reached its maximum level. If it does not increase, then no change can occur either.
However, it would soon be clear that the increase of entropy is a fundamental law of nature and is applicable to different systems other than thermodynamical ones. The increase of entropy may be considered as the measure of the spontaneous tendency of all systems to evolve towards a disordered state rather than order. According to the second law of thermodynamics, time seems to flow in one single direction, onwards and not backwards. The irreversibility observed in natural phenomena seems to contradict the fundamental laws of physics formulated by Newton and Laplace, which, instead, do not have an arrow of time. If one tried to invert the arrow of time with respect to the motion of a ball, that is, by playing a movie backwards, only the direction of its velocity would be inverted. This, however, has no effect on all the remaining parameters which govern the equations of dynamics. If this principle is valid in all elementary processes, then why don't we observe, for example, billiard balls reordering spontaneously? During the second half of the 19th century, the contradiction between the irreversibility of the second law of thermodynamics and the temporal reversibility of mechanics equations was a great problem for scientists.
Boltzmann's merit was that of exploring a totally different path, which was already present to other contemporary works. He had the philosophical courage to explore in depth what is known today as statistical mechanics.
In 1869, Boltzmann was appointed full professor of physics at the University of Graz. Fervently and enthusiastically, he reorganized the didactic activities and initiated the establishment of a new laboratory within the institute. Lisa Meitner would say of him, "He himself was so enthusiastic about everything he taught us that one left every lecture with the feeling that a completely new and wonderful world had been revealed."
In effetti Boltzmann era una persona molto
Boltzmann was indeed a sociable person, with a pleasant and gentle character, though very self-critical. This might explain the ups and downs in his life. He was willing to talk to everyone. He was very kind to his students and was very good at explaining his lessons. During the exams, he always tried not to fail his students, if possible, especially those with economic problems.
In Graz, he met his future wife, Henriette von Eigentler, one of the few women to attend university at that time as a mathematics and physics student. They married in 1876 and had 5 children, to whom Boltzmann dedicated all his love and attention. Boltzmann's works in Graz were deeply influenced not only by mechanics, but also by the Scotsman James Clerk Maxwell, founder of electromagnetism and among the founders of statistical physics. Joseph Stephan, Boltzmann's teacher, introduced him to the works of the great Maxwell. In 1855, Maxwell had already understood the corpuscular composition of Saturn while studying the nature of its rings. This was to lay the foundations for his famous work in 1867 on the probabilistic distribution of molecular velocities of gas. This idea was to be the starting point for Boltzmann's kinetic theory of gases, which formed the core of his most significant work of 1872.
Aristocrat Maxwell used mathematics with great mastery, but he believed that the calculus of probability, in which he was very skillful, by the way, was an inexact form of describing nature. Let us take as an example a gas made up of a huge quantity of particles in motion. Maxwell believed that science should be able, sooner or later, to formulate the equations of motion of each and every particle.
Prior to 1850, the concept of probability in physics was almost unknown. It was first introduced by Maxwell and then brought to its extreme consequences by Boltzmann. The problem Boltzmann had to face was that of trying to understand the behavior of macroscopic systems made up of an extremely high number, billions and billions, of particles. Boltzmann believed that it was totally useless to think that understanding the behavior of these systems by measuring every particle's position and calculating its trajectory afterwards could be possible.
In 1872, when he was only 28, Boltzmann published a fundamental work on the theory of gases, mainly focused on the calculus of probability.
It is not true that the calculus of probability excludes the understanding of the material world. The calculus of probability is, in fact, a sublime aspect of mathematics, and all its theorems are precisely demonstrated, as well as those theorems involving the theory of differential equations. The use of probability does not mean we're giving up something. But at the time Boltzmann was writing these things, he was isolated within the theoretical physics community.
In his work, Boltzmann introduced a new equation describing the temporal evolution of probability distribution. The equation is known today as the Boltzmann equation.
This equation is essential both as a basic principle of physics and its applications. As regards its principles, the equation permits the understanding of how probability changes in time, and above all, explains something that until then wasn't fully grasped. In everyday life, there is a clear distinction between past and future. In other words, events are time-irreversible processes. A classic example is the cup of coffee falling on the floor and breaking into pieces. Nobody has ever seen the opposite occurring. That is, pieces of a cup recomposing and jumping back into the hand. However, as far as fundamental physics is concerned, equations are time-symmetric. Yet when physics in everyday life is observed, it appears that this is not the case, that there is an obvious direction of time. Boltzmann was the first to give a convincing explanation of this. Watching a cup of coffee recomposing and jumping back into the hand is not possible. It is highly improbable, much more improbable than winning the lottery for every week of the year, to give an example, or much more probable than a monkey composing the entire Divine Comedy from the first verse, the middle of our life's journey, to the last, the love that turns the sun and all the other stars, by typewriting randomly. It is highly unlikely for events like these to occur, yet not impossible. The equation of Boltzmann gave an acceptable explanation for this.
Boltzmann believed that a gas was an aggregate of atoms in constant motion.
Clearly connected with atomism is the hypothesis that those elements of bodies are not at rest, forming matter by lying rigidly alongside each other like bricks in a wall, but that they are in vigorous motion.
In his study of gases, Boltzmann embraced the kinetic theory founded by Daniel Bernoulli in his 1733 Treatise on Hydrodynamics, which was later perfected by James Clerk Maxwell. Let us take as an example a gas placed in a container of a given volume and at a given temperature. On the basis of kinetic theory, the pressure on the walls is nothing but the result of many collisions of the atoms against the walls of the container. The gas temperature is a direct measure of the kinetic energy of particles. These particles do not all have the same velocity, which is distributed according to the law of probability of brilliant Maxwell. According to this theory, a temperature increase is followed by an increase of the number of collisions and a subsequent pressure increment. Vice versa, the decrease of temperature is followed by a decrease of the pressure on the walls. This theory is extremely important, as it explains brilliantly the well-known gas phenomena which until then were beyond understanding. Kinetic theory enables us to make an assessment on the size of an atom. By increasing it, the space for its motion decreases. Vice versa, by decreasing its size, the space available for motion increases. This means that simple thermodynamic measurements will allow the calculation of the size of an atom.
L'opera principale di Boltzmann
Boltzmann's main contribution was that of giving us all conceptual instruments to be able to make a probabilistic treatment of systems made up of a high number of particles. Collective behavior may then be deduced, such as the laws of perfect gases, on the basis of microscopic behavior. Theoretical assessments can then be made on how systems made up of a large number of particles behave without needing to measure each particle's position.
Boltzmann's extraordinary contribution consisted in understanding that the perspective offered by the kinetic theory of gases allowed for a convincing explanation of the apparent contradiction postulated by the second law of thermodynamics, the paradox between reversibility of microscopic phenomena and the irreversibility of macroscopic phenomena. Boltzmann suggested the example of a gas confined in half the available volume of a container. Consider a gas consisting of billions and billions of molecules. As the separator opens, gas will expand until it occupies all the available volume, thus reaching an equilibrium distribution. The diffusion process seems to be macroscopically irreversible because the system will not return spontaneously to its original state. Boltzmann's explanation of this phenomenon is simple. At a microscopical level, the motion of all particles is reversible, but the probability for all of them to return to their initial position is highly improbable.
So originally, Boltzmann said his equation is always true. But then people said, how can this be? Because if I look at the mechanical equations of motion, they will allow for reassembling the glass, making out of the many little pieces sort of back the wine glass sitting on the table. So this was a big problem for him at the time, and the only solution, which sort of, in retrospect, looks rather obvious, is to say, look, I mean, this is fine, but when I have equations of motion, I have to also tell you how to start. This is sort of what we usually call the choice of initial conditions. I have to tell you what are the initial positions and velocity of all the particles. And so the answer is that whereas the initial conditions which we see when the wine glass is sitting on the table and falling down, are easy to prepare. I just have to take the wine glass out of the cupboard and put it on the table. However, the other initial conditions, namely the glass reassembling, would sort of require an enormous precision, which of course we can never achieve. Therefore, the solution seemed to be rather simple, namely these are different conditions, initial conditions. Some initial conditions are easy to realize, others are very difficult to realize.
According to Boltzmann, reversibility of a phenomenon is linked exclusively to the ability of reproducing very accurately certain initial conditions. Reproducing the ordered starting configuration of a billiard table, for example, would require extreme accuracy in choosing positions and velocities of all 15 balls after they have been struck. If this appears to be extremely difficult to achieve with 15 balls, try imagining what accuracy would be needed to recompose the billions and billions and billions of particles of which a piece of matter such as our cup is composed. Following his work in 1872, Boltzmann published a series of articles in order to answer the wide criticism raised by the scientific community, two of which were extremely relevant. The first concerned his friend and colleague, Joseph Loschmidt, who raised the usual issue of reversibility of Newton's equation. The second criticism, much more subtle, was that of Ernst Zermelo, Planck's student, who found an apparent contradiction between his results and the Poincaré's recurrence theorem. The latter asserts that a mechanical system will always return, sooner or later, to its initial state.
Boltzmann instead gave a very clear and satisfying explanation for irreversibility. The explanation consisted in a change in his standpoint with respect to his first works, which concerned only irreversible motion towards equilibrium. Following objections, he accepted those who argued that isolated mechanical systems returned in cycles to their initial state. He, however, added a calculus of the time required to observe a possible return to the initial state. Take a gas, for example, and close it in one half of a divided room. Then remove the separating wall and let it diffuse. How long will it take the gas to return to the other half of the room? Boltzmann's calculation was very simple. He estimated the return time of 1 cubic centimeter of hydrogen in normal conditions closed in a container of which it initially occupied only half a cubic centimeter. Well, the calculated time is so long that its unity becomes irrelevant, so that a return to its initial state is theoretically possible. What is impossible is observing it, because on such a long time scale, the solar system wouldn't exist anymore, nor would the universe.
To complete this brilliant deduction, Boltzmann, in his work in 1877, succeeded in finding an explicit formula for entropy as a measure of disorder, binding it directly to the mechanical properties of the system. The larger the system, the greater its entropy. Entropy is quantified according to the system's probability of finding itself in a particular state amongst all the possible states. The states are counted as if atoms could find themselves in different volumes to which energy is assigned discretely. Boltzmann's formula is a milestone in physics and may be compared to Einstein's famous formula, given its extreme relevance. Boltzmann's formula, for example, underlies the study of black holes, amongst the most mysterious phenomena of the universe.
Tutti gli scienziati che si interessavano della seconda legge della termodinamica.
All scientists interested in the second law of thermodynamics were induced by their personal culture to study the world as if it were a continuum. In which sense? In the sense that energy changes continuously, and so does the velocity of a particle. Boltzmann instead assumed that energy of a gas particle in motion could be regarded as discretized, meaning that there was an indivisible quantum of translation energy in the particle. This means that a particle, according to Boltzmann, could have a number of energy levels and jump from one to the other, depending on collisions.
E saltare dall'uno all'altro in funzione delle collisioni.
This was a totally radical model. A posteriori, what is most interesting about it is that almost 25 years later, the great Max Planck was defeated in his program on the enigmatic black body problem and had to finally accept Boltzmann's idea of introducing a form of quantization, a kind of electromagnetic H theorem, to explain black body radiation.
Per spiegare la radiazione di corpo nero.
Bei der Aufgabe, diese Gesetze, die experimentellen
I was greatly impressed by Ludwig Boltzmann's ideas. by which I was guided when formulating the laws I discovered during my experiments. He described entropy as the logarithm of the probability of the state of gases, starting from the atomic theory approach. Successfully applying the adequate method to radiation fields could only be possible by considering radiation as also being made up of atoms, though still considering it as made up of special quanta. This theory inevitably created the assumption that they were atom beams, or well-defined dimensions of quanta, which are recognizable through measurements. At first, I was reluctant in formulating this hypothesis because it contrasted every classical atomic representation. Yet no other solution was possible. The study proved, thanks to the cooperation of many colleagues, that the theory was indeed true.
Boltzmann's greatness, nevertheless, wasn't recognized by his contemporaries. There are reasons that are deeper than mere technical ones.
The
objections regarded not only mathematics. They involved the vision of the world. In other words, is the world made up of particles or not? During the years in which Boltzmann was elaborating a vision of the world based on the existence of particles, there was a breach within the scientific community. Chemists throughout the 1800s had no doubt that matter was discrete and that it had a corpuscular nature. Science within Europe and the United States was experiencing a heated internal dispute around this issue. In 1896 to 1897, British laboratories proved the existence of the single particle, the electron, the first elementary particle. Kelvin was deeply influenced by British scientists' experiments, and once stated in front of all his colleagues, "There is only one word to sum up my scientific career: failure."
Those happy years spent in Graz quickly faded away. Following a first crisis in 1885 due to his mother's death, Boltzmann underwent a severe psychophysical breakdown in 1888, caused by the tragic death of his eldest son, Ludwig. Perhaps the weight of too many responsibilities he had as president of the university contributed to his breakdown. He was dissatisfied and insecure, and soon felt that a change was necessary. In 1890, he accepted a chair in Monaco, but soon regretted his decision and went back to Vienna in June 1894. The condition of Boltzmann's health worsened in the meantime, and his eyesight deteriorated to an extent that he could no longer read. Boltzmann was very competent even in philosophy of science and greatly influenced the circles of Vienna and Berlin. His interest in different aspects of theory of knowledge led him to embrace Darwin's theories. He would then assert that even physics, considered as a scientific theory, has a practical value and is an instrument for man's survival.
Il suo punto di vista era
His view was,
sostanzialmente
however,
quello di un
one of a
realista
convinced
convinto,
realist, opposing many scientists'
che si opponeva
idealism,
decisamente
especially ones in
all'idealismo
disguised
di
forms,
molti
such as
scienziati,
those of
in
Schopenhauer
particolare
or Mach.
anche le forme più larvate, come poteva essere quella di uno Schopenhauer.
He used to
o quella di
criticize
Mach.
all
E
philosophers,
tutti i
even
filosofi
Kant, whom
venivano da
Boltzmann,
lui in
quite
qualche
respected,
modo
wasn't spared.
criticati, perfino Kant, per cui Boltzmann mostra un certo rispetto.
Boltzmann
non venne
firmly believed
risparmiato,
that
perché
studying the
Boltzmann
world
era
was
convinto che si
fundamental
dovesse
in order to
partire
achieve any
dallo
kind of
studio della
knowledge,
realtà per
which of
ogni
course
conoscenza.
heavily contrasted with Mach,
Questo naturalmente
who used
lo
to teach
metteva in
philosophy
netto
and
contrasto
history of sciences
con
in the
Mach,
same
che
university
insegnava
in Vienna.
filosofia e storia della scienza nella sua stessa università di Vienna.
When Mach retired from teaching, Boltzmann asked to take his place and held many lectures dealing with philosophy of science.
E scrisse quindi molti testi di conferenze che si riferiscono alla filosofia della scienza.
Ludwig Boltzmann is the father of statistical mechanics, amongst the most important branches of modern theoretical physics, which embraces today many other scientific disciplines: physics of cold atoms, the study of the brain, financial cycles, and collective animal behavior. Even the work of American physicist Joseph Willard Gibbs would contribute to the formulation of this theory.
La meccanica statistica ha un doppio ruolo come quello di Dr. Jekyll e Mr. Hyde.
Statistical mechanics plays a somewhat dual role, like Dr. Jekyll and Mr. Hyde. On the one hand, it tends to be reductionist, because it starts by analyzing microscopic systems, and then passes on to study macroscopic behavior. This reductionism of statistical mechanics was counterbalanced by a discovery made over the past 30 to 40 years. Collective behaviors of statistical systems often do not depend on the details of microscopic behaviors. This means that statistical mechanics, founded on this idea called universality of collective behaviors, somehow enables the study of collective behaviors of a system of a certain type, independently of the details of the microscopic system. Statistical mechanics, therefore, enables the passage from a lower to a higher level. It is the technique of physics that makes the study of a complex world possible, through this hierarchy of levels, without the old-fashioned reductionist operation, which nobody wants anymore.
Senza fare un'operazione riduzionista di vecchio stile, che poi ormai non vuole più fare nessuno.
These general developments were accompanied by the equation Boltzmann formulated in 1872, which turned out to be extremely relevant in modern applied physics. Boltzmann's equation is used today by many people in different fields, from the most advanced theoretical physics, the study of elementary particles, to state-of-the-art engineering applications in everyday life, such as nanotechnologies. Boltzmann's equation is useful to study. For example, the action of air during a space shuttle's re-entry into the upper atmosphere, because it is very rarefied and the air's molecular structure comes into play. And so on, there are many applications, because all other particles may be subject to Boltzmann's treatment.
Va anche aggiunto che in numerosi scritti
It is important to
Boltzmann
add that in many of his works, Boltzmann raised a truly abstruse issue. What is time? If the second law of thermodynamics is accepted, and it must be, so is irreversibility of phenomena. It would be equal to saying that these phenomena move from the past to the future according to a precise temporal arrow or direction. Boltzmann faced this issue many times. Albert Einstein was said to be greatly influenced by Boltzmann's considerations. But what was Boltzmann saying? We're used to saying before and after, in the same way we say above and under. But above and under do not exist in an absolute sense. It depends on our point of observation. The same goes for before and after. From which point of view? At a cosmological level, if we consider the universe as a whole, we can also assume that it finds itself in equilibrium. Given that this is true, there is no before and no after. Then why do we observe irreversible phenomena anyway? The answer is that we probably find ourselves in a part of the universe where there is a fluctuation inside the equilibrium. We here make predictions on the future and have a deterministic knowledge of the past. But if the universe is in equilibrium, there must be a fluctuation in the opposite direction somewhere.
Se noi fossimo lì, faremmo previsioni sul passato.
If we were there, we would make predictions on the past and would have a deterministic knowledge of the future. Roughly, Boltzmann believed that the arrow of time was an illusion of the senses. This issue would later be predominant in Albert Einstein's theory of general relativity.
Boltzmann considered the world as atoms in eternal motion, and just like his atoms, for 40 years he moved continuously from one university to the other within Europe, as if he were prey to restlessness. Yet, during the last years of his life, he returned to his beloved Vienna. Vienna during the last years of the century was the cultural cradle of Central Europe. The city's smooth atmosphere of social security, of cultural certainties and of aristocratic elegance was, however, also a home for deep contradictions. Karl Kraus defined it as the experimental station for the end of the world, a place doomed to a merry apocalypse, as Hermann Broch used to say. Vienna represented a vibrant cultural experiment where the crisis of contemporary man was experienced quite intensely. This is where modern man was born through Freud's psychoanalysis, Wittgenstein's philosophy, and the works of Arthur Schnitzler and Hugo von Hofmannsthal, and the portraits of Klimt and Schiele. The lacerating contrasts and contradictions of this culture confined between brave artistic theories, a polished formal elegance and existential desperation, suicides of illustrious persons of culture were contrasted by a cutting irony, one which pervaded the entire cultural sphere, from decadent literature to painting. The result was a unique series of men, trends and works, which today are still admired. Ludwig Boltzmann seemed to fully experience these dramatic contrasts. Despite the many acknowledgements and his nomination for the Nobel Prize for Physics, firmly supported by Planck, the last years of his life would see him deeply depressed. His worsening blindness and the frequent asthma attacks sharpened his discomfort. In 1902, he attempted committing suicide in Leipzig. His depression alternated with moments of euphoria, just like the one he experienced in 1905 during his last visit to the United States. He left a journal of that trip, which he called A German Professor's Trip to El Dorado, an amusing testimony in which he describes his relationship with Californian society and culture with sharp humour.
This journey was the last sparkle in Boltzmann's life. It is incredible to think that about 1 year later he would commit suicide in Duino, where he was with his wife and younger daughter. His daughter was to find his hanged body. This, of course, was the tragic end of a scientist who did so much for scientific development.
I am aware that I am isolated and weak in this struggle against time. Yet I will do all I can so that the theory of gases will be finally appreciated. I firmly believe that attacks, critics, and all of the never-ending controversies are nothing but a misunderstanding. It would be a tragedy for science if this wonderful theory was rejected only because of the temporary hostility towards it.
1 year before his death, Albert Einstein made a direct testing of the atomistic hypothesis which Boltzmann had supported all his life. According to Einstein, observing the Brownian motion carefully is sufficient. The dance of pollen grains, first observed by botanist Robert Brown in 1824, is nothing more than the effect of the motion of molecules of water and is, may we say, so enlarged that it is visible to the microscope. In 1909, Jean Perrin carried out his experiment, thus fully confirming the validity of atomic hypothesis. The definitive victory of Ludwig Boltzmann's ideas led to great scientific developments, the understanding of the world and the laws governing it. He was the pioneer of atomism, a scientist who was far ahead of his time. He strived to understand how it could be possible to pass from an infinitely small motion to the macroscopic events of life, to understand the constant movement of atoms and their natural tendency to disorder. He tried to understand the causes of irreversibility and the nature of time.